Okay, so I may start with my introduction while we wait for the last attendees to enter the room. Again, good evening, everyone. My name is Cecilia Lasky. I'm a professor in robotics here at NUS in the Department of Mechanical Engineering. I'm also the director of the Advanced Robotics Center of NUS. First of all, let me bring you the welcome and greetings from our dean, the dean of the College of Design and Engineering. Unfortunately, cannot make to be here. He's very angry at me because of a conflicting event tonight. So we are having the privilege of having Professor Oussama Khatib here at NUS for his sabbatical. Thanks to the support of the Department of Mechanical Engineering and the Advanced Robotics Center. The head of the Mechanical Engineering Department is also busy with the same concurrent event, so I also bring his greetings and welcome, and of course the welcome from the Advanced Robotics Center, which is a center across CDE and the School of Computing, actually, to promote collaboration, internal collaborations in NUS, and through a seed grant program, and also through lab spaces that can be made available to collaborative projects. So I'm very honored to have the opportunity to introduce Professor Oussama Khatib, whom I've known for many years and admired for many years for his work in robotics. I'm sure you know his name very well. He was really one of the brilliant pioneers in robotics. He faced the fundamental challenges in this field, in our field, and developed most of the techniques. Some of them is still used today. I'm sure that many of you still use the potential field technique for obstacle avoidance. I still teach to my students, actually. He sees robotics as the science of interaction, you may correct me, meaning that a robot is a very physical thing, interacting with the physical world and with human beings. So his approach is very much human-centered, as you see from the title of his presentation as well. He has been a pioneer of haptics as well, which is very, very relevant. Recently, he started a new adventure, the Stanford Robotics Center, to promote collaboration, and to collaboration in robotics that can have an impact, a societal impact. So a model for us, for our Advanced Robotics Center also. He is, of course, one of the most influential personalities in the international robotics community, as the president of the International Federation of Robotics Research, as an active member of the IEEE Robotics and Automation Society. He has received many awards that I'm not listing, but notably he's a member, the two small ones that he put at the very end are the most important. So he's a member of the US National Academy of Engineering and a Knight of the French Order of Merit. Among the awards, a very recent one is very prestigious, the Great Arab Minds that you see there, received in 2024. So today, he'll bring us in a journey that happens underwater, together with his robot, OceanOneK. And you will learn in a moment why this K. So, ladies and gentlemen, Professor Oussama Khatib.
Cecilia, thank you so much for your introduction, your kind introduction. You know, I met Cecilia, I cannot remember, I'm not sure, yeah, we will get the presentation, but I'm talking about you. You remember when we met?
First time.
Was it I think you were almost maybe a PhD student. It was so many years ago, and it was amazing because while Cecilia was talking about me, I'm trying to remember all the things you have been doing. I mean, one of the most famous things was the octopus. And you told me the story about the incident that happened to the octopus. Which one? Which one? because it was really such a challenging thing to work with a real life animal in a robotic lab. Well, thank you very much. It's really great pleasure to be back here. I see some of my friends who I met just recently at the last visit, and today I'm going to share with you some updates, and also I'm going to discuss some further issues related to more details, so that will help the students, also the researchers in practical aspect of dealing with robotics. But as Cecilia mentioned, I also wanted to bring up the discussion about about the Stanford Robotics Center, SRC. And SRC is something that we all wanted to do for a long time, but it's really hard to realize. Robotics, we know, is multidisciplinary, and we cannot really solve big problems in your lab. You need to bring multiple people from multiple backgrounds, mechanical engineering, designers, sensors, algorithms, and also control structures. All of these are difficult to find in one laboratory. And that's why it is very important to approach challenges together. And this is what we try to do at Stanford. And we actually succeeded to build a center, the SRC, the Stanford Robotics Center, that is bringing together people from all across the campus at Stanford University to address big challenges in robotics. And this is like another view of the center. The center starts with a sort of a ceiling having a wave going all the way to an aquarium. There is an aquarium at the end of this. And here is the team. You recognize many of our colleagues at Stanford who are involved in many aspects of robotics, AI, medicine. They come from all across the schools in Stanford. We have art, humanity, theater, we have sustainability, we have different groups attending and meeting all together in this space. In fact, it's not the PI who counts, the students, the postdocs working with them. And this is what we see. Every area of the center is dedicated to a very important research challenge. And that is what we are building. We are building robotics. I mean, robotics is not just programming the robot. Robotics is about much of knowledge that requires understanding of the dynamics, of the kinematics, of so many aspects of robotics requires that knowledge. But knowledge is not enough. You need to think about the specific aspect of the design you are building. What kind of design? What kind of interaction you need? How to apply that design to those tasks for your interaction that hopefully finally end up in a real-world application that has impact on people and on our planet. So this picture of robotics is showing how we need to bring people together. And we have a lot of groups working at Stanford. I mean, in the case of Stanford, I know the same thing here at NUS. We have a lot of different groups working on specific areas, pushing the theory and the experimentation in those areas. This is great, But this is not enough. And this picture illustrates what we are talking about. We have core research. We have fundamental development in each of those areas. And what... The volume? Okay. Okay. Yeah.
Better?
Is it better? Yeah, I think so. So what we're talking about is that we have those core scientific development that it's maybe too high. I can't hear myself. Yeah. Maybe I can just lower it. So this is mechanical adjustment of the volume. And, all right. So basically, each of these real-world applications is going to require a lot of other research, starting from the core research. The core research is combining everything from the different laboratories. So we're not doing all the research in the center. We are doing only this combination needed for the challenging in the different areas, from medical to field robotics, to domestic robotic, to education and art, and all these different things that we are exploring. So November 1st was the launch. Do you hear it there?
The Robotics Center idea is really about how can we bring an environment for collaboration. Our idea is really bringing multidisciplinary research to work together with industry to create innovations that will make an impact on our planet and on people.
So at the opening, we had about 1,000 people attending this opening, and it was sort of an amazing gathering, discussing all kind of research topics, from domestic robotics, assistive robotics, human-robot interaction, new material technologies for sensing, new ways of thinking about surgery. I mean, we all know about intuitive surgical, but there are much more things to be done and new ideas to come. And this spinner that you see here is controlled with a magnet, and this magnet could be miniaturized and put inside a robot arm. And now we can do, by injecting this spinner in the bloodstream, we can do a surgery in the brain. So it is quite remarkable, all these new ideas that are coming. I will discuss ultrasound scanning a little later as an example of how we work with haptic and teleoperation. Of course, we have new ideas about how to improve Da Vinci. There is a lot of work in motion capture of human motion, but this is not only done for the art, it's also done for understanding human motion, to help athlete, to help injured person, and to also animate robots. And basically it's quite interactive. There are a lot of interactions that brings also therapy for kids with problems in communication. There are all kind of language communication with different robots. These are collaboration with the Karlsruhe Institute of Technology. There are so many other collaborations and other projects that this was just like the first day. It was, I remember, November 1st was a Friday, and we had a whole day of presentation on Saturday with buses bringing people to the center back and forth, and it was really quite amazing. So just like to summarize, what we are trying to do is really to create this bridge between research and the real world, where we are able finally to see the result of our research, but when integrated, work together with everyone else through collaboration. So I'll be happy to discuss this as well at the end of the presentation. Of course, we have a lot of companies joining. There are a lot of outreach, the family, alumni visiting. I'm told that we have about 100 visitors a week right now at SRC. It's becoming like the San Francisco Exploratorium. It is really interesting, and it's a lot of fun. There is a lot of interactive things where the visitors can interact haptically with environments and see animations and different exciting robots. Okay, so this is the title of the talk, and I believe I showed you a little bit about this robot, but I see a lot of new faces, and I'm going to go a little bit again on this introduction. I hope the sound is...
OceanOneK, a unique underwater robot.
It's good. It's funny, I don't know, not hear it here.
Several hundred meters beneath the sea. Since 2015, an American team has been developing this revolutionary humanoid. The objective is to be able to explore shipwrecks, handle relics, evaluate and study treasures with the same precision as archaeologists.
Today, robots are designed to see, but we need robots that are designed to do.
This record would enable archaeologists to excavate countless wrecks of warships, merchant ships, aircraft, and submarines from every era that have up until now been totally inaccessible. But how can we be sure that OceanOneK will withstand the extreme pressures? Or that its bionic hands will be able to recover sunken objects from the abyss?
So the Archaeologist of the Abyss is a documentary film that has been receiving a lot of awards, and we will not see the film today, but I have a very short summary at the end of the film, like about 6-8 minutes I will be able to show. Now, the film is telling the story about the expedition that we had in the Mediterranean around really the end of COVID. It was quite interesting. We were building the robot during COVID, and we were assembling this robot and testing it in the pool that was declared a laboratory because there was no one allowed to go to the pool anymore. And we were able to take this robot and deploy it in all these locations from 40 meters all the way to 1,000 meters. And it was quite amazing because going there, we needed a boat. We were working with our colleague in the Department of Archaeology in France. And here on the boat, you can see the robot being deployed. But to the left, what you see is the control room where we have the haptic devices. And with the haptic device, you are able to touch and feel what the hands of the robot are touching. And through the eyes of the robot and your stereo vision, you are able to see what the robot is doing. So this is a really amazing thing that you experience when you are physically touching, interacting with those environments remotely. And the year after, we took the robot to Deep Dive Dubai, which is an area where everything is transparent, so you can see through. And here from the control room, you can see the robot, and well, you will see it down there. And the robot was interacting with the environment, performing work, having fun, playing pool, winning. And here is a short video. So this was a really big event that brought a lot of people and dignitaries from Dubai, and it was amazing to see and allow people to interact with that robot in the water. So the robot here is assisting in a task, checkmate. Underwater, have you seen a robot doing check, chess, playing, and interacting with the public, and it was quite a performance. So what is different? I mean, for those who don't know OceanOne, I mean, what is different from many of the great robots built that allow us to explore, see what is underwater, very deep? Well, this robot is capable of manipulation. This robot is capable of interacting with the physical environment, not just to see, but to do. And that means now it is complicated. You need sensors, you need arms, you need grippers, you need to coordinate body motion and everything. And this is what was the concept. And any concept like this is going to be tested in simulation. We have an incredible environment for simulation I will talk about later for those of you who are interested in using it. And this environment allows us not only to simulate, but also to touch the simulation, to touch with the hand of the robot the world inside of which you're operating. And the whole idea is you build autonomy on a robot, but then a robot needs not only to work in known environment and to do like average tasks. You have very challenging tasks that requires the expert. Like if you think about an archaeologist will not remove any object before touching them and finding the stiffness and whether the object is really locked. They will not break it. So this is your sensor in the water. And the water is very deep in the oceans. It is not something that a human can reach. A human can reach 60 meters. The average depth of the seas is almost like 3,500 meters. So there is no way to go beyond a few hundred meters with saturation. That is like a lot of conditioning to human to reach some depth of like 100 to 100 meters, but then that's over. So what you don't see is this also on the robot. This is where the dynamic characteristics are changing and modified, and that means you need really to understand that dynamic so that you can create posture for the robot when you approach objects. So if you think about the right hand of the robot, well, it is extended, and in that extension, you are going to feel a huge amount of force. You will feel the inertia of the body. You feel the mass of the body if you hit with the arm extended. While in the left arm, it's much lighter. You just hit and the joint will move. This is very important in the way to think about how you position, you orient, you define your postures as you control the robot. The first version of the robot was deployed in 2016, and this is the setup at the time. Haptically, you interact with the simulation, and here the robot in the pool at Stanford in 2016 before the deployment, getting ready for the deployment that took place in April 2016. And the first robot was capable of going to 200 meters. We went diving to 91 meters on La Lune, a vessel of King Louis XIV. and we recovered a beautiful Catalan vase from 1664. It was a big, big thing. You can look at this image and see the history of the water. Centuries went by covering that vase. And that was a big news in France with the interest in archaeology. For the archaeologists, it was like the first time they said we had a new technology since Jacques Cousteau brought so many technologies to archaeology. Now, archaeology is huge. Archaeology is also very under a lot of pressure because with the warming of the waters, the fishery is becoming more challenging because now we are going deeper and deeper, and you have all that destruction of the seabed, distracting also a lot of the very important shipwrecks. So archaeology is a lot of pressure to restore and see what is in there. Scientific work requires a lot of also intervention. Here we were in Santorini at the volcano Colombo to help scientists in their mission of studying that volcano. The challenges for oil and gas are huge. Everything human is building underwater is built above water, lowered down, and when we have a small problem, we have to move everything up and stop production for oil and gas or stop all the communication and the things that we are doing with those structures. So there is a huge interest going on between all the different applications to maintain structures underwater. The environment, of course, is a huge problem right now, and we need hands to do things there. And the same thing for marine biologists. Marine biologists were part of the mission, and they were so excited to see the discoveries we were able to do inside some of the boats. Now, again, I'm repeating, we need to connect the human to this sensor, your robot. We need the human maybe to give high-level instruction to the robot. So you build autonomy on the robot, and as we will see, this is only functional autonomy, navigate, grasp, do things. But the bigger picture about the cognitive autonomy is not there yet. And you still need the expert. As long as we need surgeon, we still need human expert to work with those machines. Now, it's not only about underwater. It's not only about construction, not only about, I don't know, all the applications that requires skills of human requires that connection. So we are talking about creating a connection between human and the machine through an interface that is intuitive, easy to use, and brings every sense needed, from touch, visual, sound, etc. So in the ultrasound scanning, there is a lot of interesting things that you can start to see emerging for underwater and other applications. So here is ultrasound, and ultrasound is basically is done by a human, and it's very challenging. You hurt the wrist of a human very quickly. Now you are doing this comfortably through a haptic interface, much easier for the human to monitor. And do we need the human to be in the same room? Well, I mean, with a cable, maybe we can go to a different room. But with the internet, we can go to a different building, a different city, a different country. And now we are opening the way to something really interesting, because we can think about all of this and say, okay, the robot may be in one country, and the control, the surgeon, the radiologist is a different country. And then you have a loop. You have a teleoperation loop, and this teleoperation loop will go unstable very quickly because of delay. So we know that, and if you know that, you know a problem, you solve it. So how do we solve the problem? Well, it's unstable because you are feeding back a state to the system. But how about if we create two autonomous systems? If we create two autonomous systems, now the exchanges between them will be set points. And we know set points are 10 times slower than the feedback. And immediately you gain 10 times of time for the delay. So we are able to handle a second with this approach. And we proved this in different venues. And one of the ideas of all of this is, how about taking our radiologists virtually to every village that does not have a hospital, which, I mean, covers most of the planet. So now you can reach those locations with a robot that is going to do the ultrasound imaging. So your hands are in a hospital far, far away, and you are connected over the internet to this robot. Well, I mean, it could be mobile clinics moving between villages, and these mobile clinics will be calling on when needed, because the mobile clinic can perform most of the general scan autonomously. We don't need even to connect. But then as soon as we discover any trace of potential problem, we connect, we call anyone who's available within 10,000 miles can join and connect, and then now we can do the scanning and determine whether there is a problem. We did this at IROS 2024 in Dubai. Basically, we were able to touch all these robots, including one with Marcelo's lab, and students were setting up. So what we did, we have IP addresses to all these different locations, and we connect to their robots. We download our software, we connect to their robot, and then we control the robots. And you can see here on the left, you have Stanford from Abu Dhabi, then Korea, then you have Singapore, and DLR in Germany. It was amazing. With one haptic device, you are touching the whole planet. Touching, because seeing, we know we can see now across the planet with a zoom, right? but touching requires really fast communication, no delay in the perception, despite the fact there is delay because we are using the internet. We're not using anything special for this. So last month I was invited to speak at Creates in Thailand, and the Princess of Thailand was there. She was hosting that meeting, and actually she is trying the haptic here in different virtual interactions, but I mean, the radiology I was doing, a radiologist controlling a robot over at Stanford. And here is the setting that you can see in here. So the setting is this phantom chest controlled, and you can see this image here. This is the image that we have at Stanford with the robot working at Stanford. And the image is sent back to Thailand, and the remote control is done from there. And it is amazing. I mean, you're controlling the robot, you're touching, you need to perform the different approach at different angles to achieve this. And this is real. This is becoming real. I believe we might be close even to control a robot on the moon and touch it. Not on Mars. I mean, that will require much more predictive control. But really, I mean, the way we are making progress with those physical interaction at distance are going to open a lot of things underwater to handle mining, to handle many difficult problems where we can share information with colleagues across the planet. Please check this and tell me what you think about it. And then how should we move from that configuration? So essentially, what we're doing is, if it's a dangerous place, we're connecting people while distancing them, but reconnecting their skills. And this is really the beautiful idea, is now the medium is this robot capable. I mean, you can almost talk to the robot, speak to the robot, which we can do now, but still you need to touch and feel what the robot is. If you are going to buy something, you want to touch it, feel it, well, you can do that. So the internet that is allowing to see the object we are going to buy, now we can touch them and feel before even buying them. And this is a huge progress for the physical internet. Basically, we are able now to reach beyond just the data displayed, but more in the high frequency touch and feel. All right. When we apply this in the medical field, I mean, I always emphasize this. What is our major concern? For me, this is the concern: safety. How do we handle safety today? Well, almost everyone is handling safety by dealing with the programming of the system by software, by putting the sensors, shutting up the power and saying we are safe. And this is not right. We really need to create safe robots. And to create safe robots, we need to think about the hardware. So very often we spend a lot of time of work wasting hours and hours fighting with the robot rather than really making the research, because we selected the wrong robot for the task. And really, this is a message. If you remember, you really need to think about what hardware you have and for what. If we are doing physical interaction, you need hardware that has compliance. You need hardware that has sensing of contact forces, of tactile information. And what do we have today? We have a lot of robots that are becoming like more compact and miniaturized, but not back drivable, or has little capability of torque control, which makes them very bad for force control, which makes them very bad for any contact. What do? We control joint motion, and we control the joint motion to reach a location. If we make a small error, it won't work. It worked in manufacturing because we had bulky, heavy, rigid robots that were designed with fixtures to achieve that. But now it's not the case anymore. If you are in the real world, you don't have that structure. So the hardware is very important. And we are building the next generation of hardware. And this is called Maestro. And Maestro comes from like a descendant of a family of compliant robots I started working on in the mid-90s. Oh my God, this is Artisan, 1995. It was the first concept of building a compliant robot that led to LWR, the lightweight robot of DLR, that led to the KUKA that you know, that led later to the Panda that's Sami Haddadin's Franca is his daughter, gave her name to. And then my student started Flexif, which is very successful. Actually, it is one of the best robots today in terms of capability for torque control. But all these robots that are supposed to provide us with manipulation skills, they do, but not in an optimal design way. If you think about rotating your hand, a human do it like this. This robot will require to do like the whole motion. And the reason is they don't have the symmetry, they They don't have intersecting axis at the wrist. They have many offsets. All of that leads to challenges. So Maestro brings all of these, but brings also non-singularity in the middle of the workspace of the wrist, which is really a very, very big advantage because you don't want singularity in the middle of your workspace. And compared to other robots, it's much more compact, which means it's much safer. But this is not enough for safety. Safety is going to be not by software or just like the weight of effective masses of the robot. We're going to create safety by rendering the robot mechanically limited in its ability to reach beyond where danger can take place. So we're going to each of the joints, and we are going to now reprogram joint limits. By reprogramming joint limits, we modify the workspace. So we have this module that reconfigures the workspace of the robot. So let's take an example. You see this cute patient. The workspace of the robot is like this, the red. Now, before even intervening, we are going to reset the workspace and make it like this. And that allows us to reprogram, basically redesign the robot for this patient. And that takes a few seconds. I mean, we take an image, reset the robot, and now we have the robot that is 100% safe. So think about this in construction. I mean, think about the construction task that from drywalling to painting to bolting to welding. We looked at all of this, and in every case we looked at a solution, how robotics can bring a solution to those things. And this is something that is going to bring interaction with the human. I mean, it's the same thing. If we say we will remove half of the people from offshore, it's very difficult to stay offshore. I mean, we can control many things remotely from inshore. Can we do minimally invasive mining? Yes, we can do minimally invasive mining by rethinking the way we do mining. Right now, mining removes so much material, and we put so much mercury to extract a few grams of gold. Well, now we can do it with robots that are moving inside the aura and extract only what is needed. Well, in space, I mean, all the application in space. Right now, we deployed a haptic device in space, and these astronauts are controlling robot on the ground at DLR. So this picture, again, it has many features, and I wanted really to focus again on what makes all of these things I'm showing you possible, and how we came to be able to produce results. So let's take a look. Anyone knows Romeo and Juliet, beside Marcelo and Cecilia and my friends over there? This is Romeo and Juliet, and let me show. Romeo and Juliet was designed and deployed at the opening of the Stanford Computer Science building with the presence of Bill Gates and Melinda. You can see them on the left of the image. And here is the robots. Can you do this today? This is 1995. This is one of the most challenging tasks, how you can collaborate between two robots to carry an object like this or interact with the robot through, which was applied to Asimov, which was inspired by human modeling. This is done with robot models of musculoskeletal systems that are being controlled using the same architecture. And all that work on humanoid led to more work on other concepts of how to use tools with the robot and then how to use humanoid robotics for underwater. And that was the first robot that we designed. So all came all together by really developing the architecture of control to allow us to address the problem at more and more abstract layers, reaching the task level to control the robot at the most highest level possible. It's not really, there is never along all these illustration any inverse kinematic or joint position control. It won't happen because human joint position control relies on the idea of precision. Humans are not precise. Humans are capable of performing a lot of things using compliance. This is how we control the robot. Just you move the goal and the robot hands are following your guidance. The body of the robot doesn't know any joint at all. It knows only a criterion of a posture, which is a gradient descent to a goal you designed and you apply in the null space of the task. Sorry for the technical terms, but essentially, you don't do anything. You just say, move the hand, and the robot will follow, knowing that it has to maximize the range of the arm that you are using or minimize the effective mass or whatever criterion you put. So this, together with the contact, in contact we have compliance. Compliance results from this, a description of a frame. We call it the compliant frame. Do you know what frame we are using here? If we take this frame, Z force in this direction, moment about the two axes, and everything else is orientation or position control. Well, it is relative to the interaction. It's independent of where things are. So this works, and it works because not the precise motion control, it is because the touch and the feel. This is how humans work, and this is how we can learn from human. So if we want to learn really properly manipulation task, we should not record trajectories. It's the wrong thing to do. Record trajectories, you change slightly the environment, and it's over. And I'm not even interested in the trajectory of the task. I'm interested in what was behind the trajectory. What is the strategy the human was using? So we need to learn, but we need to learn abstractions. We need to learn strategies. From a demonstration of a human, what I will do after segmentation is I will try to process it, to make sense of it, to understand what was going on. And to do that, I need to take all that data, not only of motion, but of contact, of tactile information, velocities, projected on the frame, extract that compliant frame. And once I have that compliant frame, I can build the strategy that can be used in a very general way. Let AI do that. You don't need a lot of data centers to store all the trajectories. It's a big mistake we are doing today in many, many venues. We think, oh, just give me more data and I will solve the problem. No. You will have always cases where you're not solving the problem and you're not using the structure of the problem. Moving from A to B, we know how to do it. It's very simple, J transpose F. F is the gradient that takes you to 0 at the goal position. I mean, it's not the problem. Avoiding collision, we can do it with artificial potential field. This is not a problem. We can plan motion now with very fast. It's not the problem to move. You're trying to program the robot by imposing a trajectory. This is what we were doing in manufacturing in the 70s, using teach pendant. And we are going back to that, forgetting everything about what robotics has done in the last 60 years. We made a lot of progress in the architecture of control, and we should not forget it. So here are some examples. I mean, here is an assembly task. This is a miniature of the wing of 787. You disturb it, and the robot will go and perform this strategy. It is not a trajectory. It starts from anywhere and goes anywhere, but it is based on contact information. Disturb it again, and it go and place it. Here we don't have a camera for some reason, because it's transparent. I need to touch and find the contact normals. Then I can grasp, and then I can grasp it to a point where it is really properly grasped. So if someone comes and try to steal my glass, it cannot. Here is the interaction. I mean, these are student projects. Student project developing very simple things. Once we have the proper architecture, that's it. Everything becomes, this is an example. I mean, you see the human are having problem putting this teapot lid back. 1, 2, 3, done. Okay. We need to think about the software. So we need to get the right hardware, the right sensors, the right understanding of the models. But we need also a platform with which we can control this robot. And believe me, you students, you were lucky because Marcelo has the platform now. I said it to Marcelo, but Marcelo is not paying attention. Marcelo, you have Sci, OpenSci, right? OpenSci is great. OpenSci has everything you need. My students use OpenSci. I mean, with this architecture, I mean, I will show you some more examples. But OpenSci is now being also integrated with RAS and all of these things. It gives you everything you need to control your robot. Please, we need to build above. We need the next layer, so we know connection between perception and action is about dealing with the requirement of each level. At mechanical level, you need high bandwidth. There is a frequency domain. Don't forget, it's not one loop. There is the frequency domain, and unless you run at kilohertz for the lowest layers to control the task, you're not going to be able. So what do we do today? We send trajectories, and which we compute offline, and then we use the manufacturer controller to control those trajectories. We don't want to lock the joints to make them stiff so that they will destroy the environment when they touch the environment. We want compliance, but we still want the control. So the first layer is the layer of whole body control. It deals with contact, it deals with constraints, it deals with obstacles, self-collision, everything. It has to run at kilohertz. The next layer is that layer I talked about, the layer where we are building the skills. And that layer is going to run slower, of course. It's the input. It's parameterized by the features, which is good. Now we have more time to process the raw data to extract features that will be used. So, and with the next layer, we have the sequence of action. So we build the capability for functional autonomy. I call it functional autonomy because what do we have here in autonomy? We have grasping autonomy, we have manipulation autonomy, we have navigation autonomy. Do we have reasoning autonomy at this level? Not yet. We have a planner above, but all the high-level advanced thinking is going to come from human at this stage. And that's why we need the interface. So if we have the human interface, we guarantee that we can achieve the task if it's feasible. Here is my students' demo of 3 weeks using Sci. Can you hear it? Yeah, you don't know if a robot goes crazy. Cut. Okay, let's go back to, I have so many beautiful videos of balancing, of doing things. I was looking at the time, I didn't really want to integrate too many, but believe me, in 3 weeks, the students are able to do things that even research labs cannot do. If we get the right tools, if we get the right hardware, if we get the right project, because we discussed the project. That starts in April and goes to June, and if you come to Stanford in June, early June, you will see some of those projects. A very exciting project indeed. So let's go back to OceanOneK. The OceanOneK project, as I said, was redesigning really fully the robot to deal with the deep dive, 100 times atmospheric pressure. Completely different foam material, completely different ways of organizing the whole system. And very quickly we were able to demonstrate the robot in the pool at Stanford, designed a lot of cameras and tools, and then we took the robot to France, La Ciotat, which is near Marseille, deployed on Alfred Merlin, our boat, and there you have all the support. So when we deploy a robot, don't think it's one robot. You deploy a team of robots. You need the cameras, you need light, you need support, you need the relays. All of that makes it very, very complex. And here is, again, the control room with your hands in the water, your eyes on the eyes of the robot. And now the robot is diving to 40 meters, deeper and deeper. Aleria is at 330 meters with a 2,000-year-old boat. And here is like the treasure sitting there. No one is able to go there. Look what we brought. This is a cup from Rome. Beautiful cup, brought back without breaking it. And the archaeologists were like just amazed. Oil lamps. Actually, the archaeologist said was able to read the address on the back, and it is an address in Rome. And maybe we can order it through Amazon or something. I mean, the biologists, marine biologists, were very keen about having pieces of this coral, the white coral, very fragile. We brought a few pieces of the boat that were left still after 2,000 years there. And this is the control room. This is the camera that we used to explore the Crispy at 500 meters. It was amazing thing. I mean, here is Ken. We went diving to reaching the bottom of the sea at 1,000 meters. And the robot kept going 850, and we were scared. I mean, we thought we lost the robot at one moment. And the robot kept going all the way to the bottom of the sea. So before this segment, I would like to turn off the light and make sure that we have the... Can we turn more the light? Because this is part of the film. It is about 6-8 minutes. I will show you, and then, so if we can turn off the light. Off. Good morning. This is at the end, we can put it. Yeah, very good. Yeah, that's good. That's enough. Okay. All right. All right, let's hope the sound is clear. All right, you're ready?
In the course
this is too bad.
50 meters. As the sun.
Yeah, it is maximum. You know something? Every time I try the sound, it is a problem not only at NUS, everywhere. I don't know why. We solved all kind of things, like we can fly all across the Mars, and we still haven't solved the problem. Okay, I'll turn it up. Okay, we try again.
In the course of 5 dives in the Mediterranean, OceanOneK will be pushed to its limits and attempt to reach a depth of 850 meters.
The other possibility is maybe I can take it from here.
As the sun rises over the border of Bastia,
Let me try this. I need to get the
Maximum here.
sound.
Okay, this is already out.
No, I will take it from the speaker. So I'm going to try to take it from the speaker with the microphone here. Yeah, you should shut the...
in the course of 5 dives in the Mediterranean,
Is it better?
OceanOneK will be pushed to its limits and attempt to reach a depth of 850 meters.
Okay, we should go.
Sorry.
We need more engineers, please.
You want to play that? I think just now. So.
I'm changing back the sound system to this,
Yeah.
but still it is.
You can try. I reduce the feedback already.
Okay, let's try one more time.
In the course of 5 dives in the Mediterranean,
No.
OceanOneK will be pushed
Huh?
to its limits and attempt to reach a depth of 850 meters. As the sun rises over the port of Bastia, OceanOneK sets off for its next challenge at a site well known to archaeologists, a wreck known as Ilaria 1. After an hour's descent, the robot archaeologist is now 330 meters below the surface. That's almost 3 times deeper than the previous record for human underwater archaeologists.
The lights are just under your left hand.
He'll try to pick up the first piece.
Okay.
Can I let go now?
I think so.
When you're ready.
Okay, it's in the crate.
Bravo!
That one. That one. You have to turn a little to the right.
Turn, yes. Look, look.
It managed to retrieve 4 Roman remains without damaging them. It's an unprecedented success.
Take it out gently.
Success is the culmination of almost 10 years of work by a Franco-American collaboration led by two men. Oussama Khatib, an eminent roboticist from Stanford University, and Michel Lourd, an archaeologist and director of Bracel, the organization responsible for conserving the underwater archaeological heritage of the entire French maritime domain. OceanOne is about to explore one of these endangered metal wrecks, the Francesco Crispi. After an hour's descent, illuminated by Hilarian's lights, OceanOneK comes face to face with Crispi. The wreck was discovered in June 2015, nearly 70 years after the ship went missing.
Okay, the camera is going in.
Carefully, OceanOneK manages to insert its camera into the wreck for the first time.
Ah, that's great.
So, are we trying to get into the living quarters?
Yes, on the left.
For Michel Lourd and Oussama Khatib, it's a big first. Thanks to its revolutionary humanoid form, OceanOneK can squeeze into the tightest, most inaccessible spaces.
We're going back down.
It'll be tight.
Very tight, yes.
Moving carefully, OceanOne ventures inside the wreck. Something no robot has ever done before.
And I'm going to go out back.
We'll take 1 or 2 photos below, then go back up.
OceanOneK completes its perilous but successful mission.
Got it, thanks.
In the Bay of Cannes, OceanOneK will now attempt its most difficult challenge yet, reaching the incredible depth of 850 meters.
We are very excited about reaching a new milestone in depth with this robot.
Little by little, the humanoid inches its way towards the seabed.
And
I'll go down and feel around here.
underbody, yeah.
Like commemorating the first steps on the moon, OceanOneK has taken along a plaque to place on the seabed.
We're going to hit the ground. Yeah, I'm going to hit the ground. Yeah, we touch down. We touch down. It's amazing.
You're at 850.
After a descent lasting a little over 1.5 hours, the robot finally reaches the seabed. The robot has successfully completed 5 missions, demonstrating its stamina, dexterity, and powers of observation. Those who came up with the idea many years ago feel immensely proud.
Bravo! Well done, buddy.
OceanOne came to Cannes and carried off the Palmador!
This incredible mission is a world first. one that opens up a whole new chapter in underwater archaeology. Thanks to this humanoid, archaeologists now have access to thousands of unexplored sites, buried wrecks, and sunken worlds. It gives them the incredible power to make the ocean reveal its mysteries.
All right. I guess we need now to work on a new project related to sound. that would be really good. Yeah, this was amazing. I mean, just you have to imagine this was done over almost the 2 years, 21 and 22, because of COVID. We had all kind of regulations that we needed to take care of, and the boat was not able to go without certification of sanitation and other things. So my students were really excited. Like we would go in 1 month, and then we return, and then we go again later. I think we were there 3 times. In September, in January, and we ended the mission in July 18th, 2022. And it was like incredible for every student spending the time on the boat and spending a lot of time on the islands and tasting the very nice seafood of France, in the south of France, and also in Corsica. So they are asking me always, when are we going to go next? All right, well, I'll be happy to entertain any questions. We maybe have a little bit of time for discussion, right? Okay.
Thank you so much. Amazing as always. So who has questions?
Yeah. There is one here, one
I
there.
don't see. Raja.
Hi, Oussama. Thanks for an amazing talk and really inspirational one at that. You had a nice architecture for collaborative human-robot interaction, right? And I saw that there was one block which was world model. What kind of world model do you see, like perception pipeline building, so that human robots can interact better?
Yeah, this must be someone working in computer vision, right? Yeah. So very good question. So the architecture is really an architecture of abstractions as we move. Like we take raw data and do some small filtering and use it in real time very quickly. Then we extract features needed for the skills. Then we need to update our model. Already you have a model, and you take that, and that takes longer. So it makes sense. I mean, in a way, you are taking time to process the data. The data needed at the control of the physical system going at kilohertz. And as we move up, so if we look at that architecture, we see people from computer vision, from graphic, from control, from reasoning, from design. I mean, this is, that's why the title is an architecture for collaboration. And so what you are looking at is the real-time thing, but behind it, to fill these boxes, there is a lot of work to find the skills to develop those pieces that are going to be needed. So what we did, we completed mostly the whole body control. The whole body control, there is a lot of models. I mean, when you look at the software of OpenSci, you can find all these models about operational space control, dynamic models. You have models about interaction, collaboration, you have virtual linkage, you have constraints. So you have a lot of artificial potential field dealing with constraints. You have boundary layers around the zones of influence. I mean, there is a lot of structure, a lot of things going on, but all hidden for you. You just program at much higher level. And this is my message: is it is time to go with abstraction, and at that level we have a high-level picture of the model of the world. Much of the details are down at lower level.
Are there questions?
There was a question. Oh yeah, here.
You get closer.
The microphone.
Hi, thank you for the talk. I was wondering, I hope I didn't miss it actually.
Louder.
Oh, I hope I didn't miss it actually from behind. Is there a specific reason on why the diving robot is human-shaped?
Very good. Yeah, I was waiting for this question. Everyone asked this question. So I mean, at least one in every presentation I had and showed the robot, I have this question, which is really a good question, because I personally would prefer an abstract robot. Like you could have a lamp and like it's moving and like picking things, and that would be fun. The problem is, if we really want to do real things, you need a gripper. But in reality, you need two. In unstructured environment, you don't have fixtures, so you can put your arm behind your back and try to do things in the real world. It's very difficult. You need two arms. If you need two arms, when you move to manipulate, you need your cameras to to show you where you are, to see your hands with respect to the environment. This is the condition, so we navigate relative to the environment. So you need two cameras, you need to move these cameras, and you need to move your hands. What do we have? The upper torso of the human. Now, there are other reasons. The connection with divers, with archaeologists. Archaeologists who swam with the robot, they loved it. He said, this guy looks like a little child trying to become archaeologist and learning from me. And I was like on the other side, like a leader. So basically, I was feeling as controlling the robot, really I was diving almost like it's so intuitive to use your own body map in the water and interact with it. So in this case, I really concede that the human shape is fine, but it's a mermaid. It's not human, right?
Okay, maybe one last question. Okay, Ian. Maybe two, okay.
Thanks, Oussama, for the very great talk. Always learn new things every time you listen to you. The question I have is on the Stanford Robotics lab portion, right? So, I mean, you mentioned about you want to move, people together to do impactful research. Right? And we also understand that all PIs are like cats. So what's the secret sauce of herding cats to create impact?
It is so hard. I mean, it's logical. I mean, every PI, every faculty has so many problems, finding funding, promoting your work, doing, I mean, we have a system, academic system, that promote individualism. And suddenly we're telling people, come to work together. So it is really difficult. But reality is also we have people who really care about the field. And the truth is there is no way one group, one lab can solve the problem. You really need to collaborate. So we, NSF and every government agency, funding agency is promoting that. Let's collaborate. So what do? We tell them, we want you to work together. Okay, we write a proposal together. We send the proposal, accept it, we get the money, we split it, we go our ways, and at the end we write the report together. This is not real collaboration. So I'm not really interested in that kind of collaboration. I'm trying to do something different where we are motivating faculty to send students to work with multiple advisors on project funded. So they have fellowships, they have basically support. So these are like, you still do your research, but we are giving you this option to participate. Not all the faculty are at one time involved, but this model seems to work, especially when in robotics where you need infrastructure. I mean, you need a lot of idea, and suddenly the students are the driving force. I mean, we give the student the project, and they go and like start, and you hire a postdoc, and then you want to hire even a full-time engineer to guide the project, because it's really progressing. I mean, we have project with ReachBot, which is a robot. You throw, the robot catch something. Now I'm using it to put light on ocean. I mean, there are so many things. With MIT, even we have collaboration with IT in Italy. With a lot of people will come to collaborate if there is motivation. And I think we have to create the motivation, right? Right? All right. Okay.
Thank you, Prof, for the great talk. So my question is regarding the teleoperation that you had. So how did you account for the delay?
What application? Please slowly, because the tech is...
Okay. I was asking about the teleoperation. The teleoperation of the robots.
Yeah, I get it. Yeah.
So in that, how did you account for the delays that were happening? So let's say there is loss of connection, infrequent.
Yeah. So it's not teleoperation. In teleoperation, you go unstable within 300 milliseconds, 250 milliseconds, no way. The reason in teleoperation is you return a state and compare, so you are controlling with feedback. And you know the problem with feedback. If you put delay, you're going to unstable. What we are doing is we are removing the feedback. We are removing the feedback by creating a different problem. We are saying the robot is controlled all the time. All the time is stable. It has an input, desired position, force, and it's stable. The haptic device is displaying a given state. It's stable. It's running. And the two are exchanging information at a lowest rate, and that is acceptable because, you know, a feedback loop, if you send an input, it cannot be as fast as the loop. So it has to be like 10 times slower, 100 times slower would be fine even. So this is where we are working. We are exchanging set points. These set points are called proxies. And they are proxies of the real set point. And this is a technique we developed in haptics. You have to go back to the proxy of the haptic display, rendering, and all of that, and then you will find it. So sometimes ideas comes from things you have done in different areas, different objects, and it works very well for you. And this is the idea that we have. Well, I think the time is running. We will have an opportunity, right? Okay. So I know there might be more questions, but we can discuss.
Really, thank you again, Oussama, for being here, for staying here 1 month plus, and he actually interacted with many students. I hope some of them are here now, and really thank you so much.
Thank you. Thank you. Thank you very much. Thank you.